Okay, good afternoon to all of you. Uh, Today is actually we are just will have a small demonstrations. Yesterday we couldn't continue due to the technical problem, but today we'll be just going ahead. So yesterday, what we had thought like we'll be doing a small exercise. So instead of writing the whole portion, due to the time constraint, what I've decided is that probably we'll just work out and see the effect of or the steps involved in uh, image classification. So all this code again will be posted on the GitHub post. So all of you who are interested in carrying out this activity can do it at a later stage. Okay, so in first case, if you remember, we had the first class, our first lab, we have dealt with how to deal with different data sets. So those preliminaries exercise will help us in doing that, or basically the will be again required, especially to get the information about the initial data sets, because we are dealing with satellite imagery. So to deal with satellite imagery, read and write operations we carry out with the help of GDAL library. So there are also an other libraries as well, raster IO and others. But since we have kept ourselves to the GDAL introduction, so accordingly we'll be following it. So just to recap, that we'll be using this library, and then we'll be using few of them over here. So especially the cases to deal with data sets. So over here, we are going to use all these functions which may be requiring in our case. So all these, especially the data set providers, the corresponding number of rows and number of columns, and correspondingly the sizes. So all these functions will be using it at later stage. So let's directly go to the sections of the requirement for using CNN classifications. So in the CNN classifications, what we will do is generally the CNN classification scheme, which is available in form of machine learning libraries, those analysis is not being carried out in a very large images. So like in the satellite imageries, you might have seen an example. The size is approximately 3500 by 3500 size. So it is quite a huge, basically the file size. So generally the machine learning problems or all the machine learning libraries doesn't work in such a large size of images, because there is a hardware limitation. So if you want to deal with such a large images, then in those cases you have to first of all need to have a very powerful GPUs, which would have a lot of gigabytes of memories, that were also in hundreds of gigabytes of memories. So that may be the requirement to deal with. Then also, if you are using a large extent of an image, then in those cases, what may happen is that the number of features might be quite diverse. So generally in any kind of machine learning, or especially in the CNN learning approach, we try to find out a feature which can be consistent across multiple sample data. So if you deal with a single image of such a large image, then the only thing which you are left with is the ANN classification scheme. But if you want to do a CNN classification scheme, then you have to look for a way where you can get the information at smaller basically filter size, and each of those filters are supposed to be containing the specific information that may be stored as a part of your features, which can be used for a classification. So that's why what we need to do is we need to break down a larger image into a smaller one. So generally we do that by creating the types. So the standard size of any image classification algorithms, which has been implemented, or architectures, which is available in libraries like Keras or PyTorch and so on. So they deal with the image size of 64 by 64 or 128 by 128, or in some cases 250 by 256 cases. So you should have a provisions to break down that large image according to the input requirement of your image. So to do that, what we do is we are creating this small function. So what it does is it's basically takes the input file, and it basically creates the tile grid, and finally it saves the tile grid output in a form of basically attaching the number and basic suffix after the file name. There will be suffix will be attached to the extensions, and you'll be having a few data sets created. So this basically tiles job is, or this functions basically is that take a large image, satellite images, or maybe the georeferences images, and break down into smaller window size that is being defined as D. So whatever D you will pass on, so D is 64, so it is going to give you the size of the images in 64, or if you 256, the size will be given at 256. So that particular size of the windows will get clipped from images, and the whole image will be broken down into these small pieces. So this particular functions, we are defining it here. So we are already defined GDAL, and then we are going to define the functions which is going to give us a tile. Once we are having that tile available to us, then what we will do is we'll take an input satellite image and pass it on to create a multiple small size of basically chip which will be used. So over here, if you see, I'm calling this tile function over here to create a chip size of 64 by 64. And the total output will get generated, and that at later stage will move it into the input folder. So we'll just run this. Now you see that this basically what is trying to do is it has read, or it has started creating the smaller size or the chip size. So as you can see, at the suffix we are having 00 windows, then it starts from 0 to 263. So next window size is again 0 to 64 and so on. So it means like on the first row it is broken down into that satellite images is being broken down into smaller pieces. And these smaller pieces is going to be computed, and the final result will be stored. So if I see it here, so as you can see, this is generating the different tiles size. So this process is still going on. Yeah, so this is, as you see, there's size is getting increased. So there will be enough tiles which will get created. So finally what happens is this whole process is going to give a small number of tiles which will look like input indexes. So what I have done is I've taken all those smaller tile size of the images, and these images or those tiles index is actually a small piece of this one square box is actually a one tile which is represented over here. So we are, let me see if the process is complete. Yeah, this is still running. So this is going to give you all the different tiles which will get created. Just wait for some more time. In the meanwhile, let me show you the input images which we have used over here. So in this example, what we have done is we have created a image which will so in this case we are having a footprint of satellite images, so which is actually as that Landsat images, whatever we are seeing it over here, and corresponding classified map. So this classified map is actually so this is basically a Delhi region. So this is basically a Delhi city, which is you are seeing it over here. So this has been classified into different categories like water bodies, forest, urban areas, and so on. So there are multiple classes which has been created by doing a manual interpretation. So after the manual interpretation, you get this different classified images. So after getting this classified image, we have rasterized this, and this raster images actually will be used for training purpose. So this is a training images which are going to use it in the current session. Yeah, so this image is now ready. So what we will do is so this basically we are putting it all the file which has been generated by this tiling under the tiling process into an input file. So this input file is actually containing, this folder is going to keep all the images or the chip which has been created it over here. So let's go to the input folder. So the different chip which has been created, a smaller size is now available over here. Now let's open the satellite imagery as well. So this is the satellite image. So this is satellite images which we have downloaded it from the USGS website, and this is having all the information. So just create an FCC. So as you can see, this image is having a different features. In the meanwhile, you also might have observed that in this image there are a lot of lines where the information is not present. So this is basically a line drop in the images or the error during the image acquisition. So after 2003, the Landsat 7 is having a very unique characteristic of these lines where due to the failure of the sensors, this particular information at 1 pixel line is not available. So this information or whatever satellite image we are having, we are going to use this particular satellite image for carrying out the classifications. And after the classification, what we expect is that it is going to have basically the classes as depicted in this particular image. So this is the level or output images, and the corresponding input level images is this one. So this level image chips already we have created, thus we have done now. So now what we will do is we'll just go in for creation of the label images. So in this case, actual level images, as you can see, the classified image is being provided over here. So this classified image is going to create, again, the levels or the chips will get created. So let the process continue. So after creation of these images, then what we will do is we'll start basically taking all these images into a smaller group. We are not going to use the whole satellite data set for the CNN classification, but rather than a set of data set which we are going to use. So what I had done is I have just taken the small section of all the grid lines which you see in this case, and the places where built up has been identified. So in the case you can see this blue color which is being shown over here is actually a built up area. So all the dominant area over here and non-built up area in these regions, there are a lot of non-built up areas or agricultural land which is available over here. So we have taken a few sample of these data sets, and only small section of these tiles which we have seen will be used for training purposes. So we are not going to use each and every sample or every grid location which has been generated due to the 64 by 64 images, but rather than only with the images where we think that there's a dominant features of one type and there's a dominant feature of another type. So we have, as we should be aware that in your sampling cases, the number of samples which you should use for any kind of classifications should be almost equally balanced. If your data set is an imbalanced, means that there are very large number of classes of particular type, and in those cases what may happen is that you may get a trained model which may be biased towards the data set which is dominant. So to avoid that, we are doing a subsampling of this. To do that, we have created all those subsamples and corresponding informations or the has been stored. So this is basically the a list of files where we think that can be is containing the actual input images and corresponding levels. So this ensures that your data distribution is as per a subset of these samples. That's what we are creating, and we are putting it into a CSV file. So yesterday we are supposed to do this up to this exercise to create a sub data sets and then create a CSV files. So once we have created the subset of the CSV file, then what we will do is we'll read all of them and start storing the data sets in basically for training purposes. So for doing that, we are going to read this tile file and get the detail of the number of bands which is present in each of those chips. Okay, so let me import the flow. So see what is the first in the image. Okay, so this is not pointing in appropriate place. So this is a so okay, so we are using data sets to open it. Anyway, so we'll execute it and fix it at later stage. So generally what we are supposed to do over here is that we are going to open the small chip over here, then get the detail of the corresponding rows and column and number of bands for the image. And once we are having so this list is going to contain all the detail of the file, which is present in that CSV file. So as you can see, it is containing all the information about the location of the file and corresponding images. So these informations, what we are going to use is we are going to basically read that file and finally get a number of bands, and then it will get we will get the band or the chip size stored in this particular format. Then once we know that each chip size, which is 64 by 64 and then corresponding 7 bands, we are also going to store it in an NumPy array. So that's what we are doing it over here. So for each file, we are going to have a NumPy array with number of bands and number of rows. That's what we are having it in features and corresponding output level. So in the level, we are having only one band giving the information about the images. So in this two features and corresponding number of bands, what we do is we start storing the information present in the in basically the different chip which has been listed in the images. So as you can see, this is basically an image list. So from this, let's say for example, in this case, this is chip number 2240 and 4928. So from this chip, the information will get stored in an index number 14 with respect to and corresponding rows, columns, and number of bands will be stored. So all these will be a part of your features. Similarly, in case of labels, so labels are actually is being represented or will have a prefix like subset 2005 and corresponding chip number. So these two will get stored, and based on these two stored informations, the feature and label NumPy sets will get created. Once we have these details, then we can look into the basically the number of features available to us. And we can also visualize it just to have make sure that the corresponding images is being created. In these steps, so till now we have done two steps. One is that taking your image and creating into a smaller chip. And second step is that taking your data sets and organizing it into a feature and corresponding input number or numpy. So these are the two steps which we have carried it now. What now we will do is like within the features, we have to identify that which level we are going to train. So in the current case, we are going to create a simple convolutional neural network, which is going to do a classification in two categories. One is that a built-up area, another one is a non-built-up area. So in the sample image, all the area which was shown blue color is actually having a symbol 2. So that's why we are looking or we are comparing that built-up features should be the cases where the labels are actually 2. So all the places where labels are 2, only those labels should be extracted and should be put into a label feature. Rest all of them actually can be discarded. Similarly, in case of all the places in the input feature also, we are going to have subset it into a built-up features. Non-built-up feature are there where the built-up feature is not present. These two things which we are combining and we are putting it as an separate classes. And then we look for a test or samples where these built-up and non-built-up area can be categorized. So after doing this, what happens is like in your there is a kind of classification of the image where it gets categorized into two parts. One is where the built-up is present, and another one is where built-up is not present. So if your CNN network are supposed to do the classification just giving 1 and 0. So 1 means built-up is present, 0 means built-up is not present. So in some cases, what we do is in all the place, as I was telling, that to avoid the large sampling error of or bias sampling error, what we do is we simply take a small portion of the input features where feature is present, and as well as same time we'll also make sure that non-built-up areas are also being selected in the same ratio. So that's what we are doing it over here. So we are creating the places where the samples are having a built-up and non-built-up areas of equal record. So after doing that, we do a kind of combination of these two information. So it basically ensures that in our feature and input feature level, basically you have an equal number of classes and non-present classes. So these two are actually presented in the same numbers. Once we do that, then we have to do a normalization. So generally this is actually 16-bit images. So what we do, we just make sure that it gets normalized into 0 to 1 range. So that's why we are taking all the input feature and dividing it by 250 by 255. So it ensures that the 16-bit data gets normalized and the output value is always present between 0 and 1. And that's what we are doing it in this case. Once we have done and this normalization is required, because if you don't keep this normalization, then what will happen is during training process, your weight will fluctuate quite heavily. So there will be a quite large number of weight fluctuating, and there will be unnecessary computational time increase will be there. So to avoid that, the best practice is that you make sure that your input feature is actually having basically normalized values, and this is due to at a transition level, which is 0 or basically the activation functions which are quite sensitive near to the values of 0 and 1. If it is goes beyond 1 or less than 1, then it is not as sensitive and the corresponding weight operation will also be lesser. So that's why we should make sure that your data sets are actually normalized. So we are going to do a normalization of this data set over here. So this ensures that your label feature is ready along with the input features, which is normalized. So it means this is basically a third step where we are finishing. So the first step we're taking as satellite image and creating into, second step is creating a multiple chip. Third one is reading all those chip and storing it into a normalized two format, input and output. So that's what we are doing it over here. So once we have done it, then what we'll do, we'll simply take all these samples. So in around 3,000 different chip is present in this example. In this example, basically we are going to have, or basically we are going to create a sample which is 0.60 degree or 60% is actually will be used for training and 40% will be used for testing. So that's what we are doing it in. For doing that training and testing purpose, we are splitting it into two portions. So based on this, what will happen is that we are going to create randomly selects the from the input feature and the corresponding labels. We are going to create data set in such a way that there is a kind of randomly 40% is being made sure that is actually a part of training, and 60% is actually a part of training, and 40% is part of basically the testing phase. So for that, we have defined these functions. So this function is basically going to take an input features. Then there's a basically a random selections, and so that we get features based on the randomly generated indexes to ensure that we are having a train X testing and training into broken down into two groups. So that's we are having here. So after that, what will happen is our data set will get broken down into two subcategories or two subsets. One will be the training, another one is the testing. So this step 4 basically the strategies to create the or break your total samples into smaller portions. Once we have this train test data set available to us, then we are going to use it for modeling purpose. So in this case, we are using a library called IIRS. So for that, we have to import the IIRS library. And IIRS library is actually a machine learning library provided from the NVIDIA, supported by Google and other different companies. So with this, basically, you will be able to create a very complicated, large networks, and that can be used for creating a output data sets. So to create an image in this case is very easy. So what we have to do is we have to create simply a framework, model framework, and then we have to create a convolution filter. So in this case, we are creating the total 32 different convolution filters, and which filter size, or basically filter size, is having just one. So it means only 1 by 1 window is being used for creating the 32 filters. So it means like there will be 32 filters will get created of window size of 1. So that's basically ensuring that if any specific informations about the geographical boundaries between city and non-city is existing, so that can be easily done in this case. So with this 32 different filters based on the input size, so it means like 64 by 64 in our case, along with these 7 bands, we are going to take the input, and corresponding first convolution network will get created. Then we we create a second convolution. So it means like there's a second convolution network or second convolution filter is being added to on the top of that. Then again, in between these two stages, there is a special layer which is called dropout. Now in the dropout, if you remember in the lectures also we discussed that in the dropout case, what happens is that you may be interested in generalization state. So it means like you don't like your network to be too particular about the specific data sets, or to avoid the overfitting, the dropout is one way of correcting that. So in this case, what happens is during the training process, any one of the or randomly selected the link or the weightage will be put down to zero values. This means basically switching off the corresponding output from one layer to the another layer. So that's what the system or the dropout function does. So you just need to specify that how many of total connection in your network should get dropped. So in this case, 25% dropout we are accepting. So there are two convolutions. Then there has to be a drop of or the features which has been learned under the convolution features. The corresponding weight will be whenever we are going to use those weights. Out of those convolution and weight, we are going to basically drop the 25%. So that's what we are doing it over here. So these 32 filter first gets created. After the first 32 filter, there is an output generated. So there's a second stage where 48 next filter is getting created. So after two simple convolution layer, then what we do, we connect a fully connected network. So that basically ensures that the total 64 by 64 input features, whatever the input is generating, all of them are getting actually as a fully connected dense network. So it means like there will be a full connectivity between all these 44 by 48 by 45 nodes and corresponding 64 fully connected networks will be generated in this case. So once we are having this fully connected 64 dense network, then again we are having a dropout of 50%, and finally we generate a softmax giving the output in two range, which is basically value between 0 and 1, and that's being controlled by with the help of activation function ReLU and corresponding softmax function. So softmax function will ensure that our output is actually in two different categories. That's what, after the unbundling and then creating a two process output, the corresponding model is complete. So once we are having this model created, so this model will actually look like that, will be like so it will be having a structure where we can say that there will be a input, so 64 by 64 by in our case we're having a 7 bands, so 7 by 7 into 64 input size will be provided. Then we are going to use then it is going to have a 32 basically convolution networks, and then 48 the next layer, so 2 layer after the input, 3rd layer, and finally 4th layer. So it's basically a 4 layer with 2 output will get generated. So in between you are having an input and output layer. On 3 in between you are having an basically the models available to, or 3 different intermediate hidden layers are made available to you. So once we have this model ready, then what we need to do is we need to train. So that is being done with the help of model fit. And if you see in this case, whenever we are creating a model for training purpose, then you have to define a kind of differences. So in this case, we are just dealing with 2 categorical data sets. So we are saying the sparse or basically categorical cross entropy is the functions which will be used for creating the losses, which will be used for back propagations. And for that, we are going to use the optimizer. RMS is the optimizer. So RMS proportion error will be used for optimization. So last time we have seen a formula where E was actually an expected output minus actual output. So same RMS error will be used in this case as well. And basic accuracy of measurement or computing of the losses, we're going to use the metric accuracy. So once we have created this model, then we can fit it. So after that, the total data set will get executed only on the training sections. And once the training is complete, then we can use for evaluation of its own data set based on the taking same as same input and corresponding same output. So for that, we are using actually a confusion matrix library available in sklearn, and that with that we are using, or we are extracting different scores or metrics for generating the evaluation matrix. So once we have that evaluated matrix available to us, then we can compare it with the result, and that result will get generated in a computing of the confusion matrix, which can be used for evaluation of your models. So this will ensure that your prediction, your testing samples are actually getting, or your model is actually ready to execute it. So during the training phase, you use the training data sets. During the testing phase, you use the test data sets. So it means the other 40% of the classes will be used for classifications. So after that, what you do, you evaluate the result, and finally you save the output in a corresponding locations. So this is basically giving, or it's going to give you the output in form of model file, which can be used for doing a prediction. So for doing a prediction at later stage, so all the exercise of training needs to be done just once. So once you have this trained model available and evaluated, and you say that this is the maximum result which was expected from this network, and you have got those results, then simply these trained models can be used for predicting a new data sets. So to create a new data sets, whatever input satellite imagery is there, you have to again break down into a smaller chip using the tile functions as we are having earlier. Then each of the tile objects again needs to be passed on, or each of the satellite images has to be again converted in the form of features, as we did for the input case. And finally, what may happen is that we can use each of those chips to generate the predicted image, and corresponding predicted image output can be stored for in specific chips, and output can be generated. So to generate a final result, all the outputs again needs to get integrated the way we are having a script. So we have to reverse that particular split which has happened at the beginning, and all those 64 by 64 chip individual images will get stitched together, and we'll be having an output satellite imagery output results generated in the data sets. So this basically is just the example showing the flow of the different steps involved in CNN. So the training will require a bit of time, so that's why I'm not executing all the code, because there may be some resource constraints. So, but in any way, you can try it out and download the data sets and try it out at your laptops according to your convenient time. And once you have done that, then if you face any issue, please mail us and we will try to rectify it. But I hope that with this availability of this code, you will be able to run and execute it for any particular type of images. So with this, we are going to end the current session. So if any questions is there in the current session, then we can take it. And at 5 o'clock, we'll spend around 10 minutes to cover or ask or any feedback which you would like to provide that can be taken at the 5 o'clock. So just post your questions related to KRS based CNN classification scheme, which we discussed now. And later stage, we will be again after 5. If any doubt is there related to all your modules or if something which you want to ask or have any specific query across the whole lectures or whole course, that can be taken at later stage. So just post your course.